Hello, my name is Dr. Sean Teague, and I am a cardiothoracic radiologist from Indiana University in Indianapolis, Indiana. And today we're going to discuss cardiac volume and flow measurements. I have no financial disclosures, but I do want to disclose that I may have a few mathematical equations that I present during the presentation. I'll try to keep these simple and not use complicated formulas such as those seen here for K-space. I want to start with our learning objectives because, as Yogi Berra once said, if you don't know where you're going, you might end up someplace else. So I think it's a good idea for us to keep our learning objectives in mind when we're going through the presentation. So here are our learning objectives. After the presentation, you should be able to prescribe a scan for flow and functional analysis, perform the actual flow analysis for vessels and valves with stenosis as well as regurgitant valves, perform functional analysis of the left ventricle, and list at least 3 clinical use case scenarios where flow and functional analysis would be performed. So let's get a little bit of an idea about the audience. How often do you perform flow and functional analysis? Daily, 2 to 3 times a week, once a week, 2 times a month, or once a month? So now let's talk about image acquisition and processing. So as you likely are aware, phase contrast imaging is what we're going to use for flow analysis. That's because phase contrast uses a phase shift to allow velocity encoding of the blood, and this velocity encoding is proportional to the phase shift, which makes it easy for us to look at the phase shift and determine the velocity of blood. The good thing is that MRI is much more reliable than ultrasound in the fact that it is not limited by an acoustic window. Now, ideally, we would have a calibration using a flow phantom. However, this appears to be an issue of the past. In general, we don't have to worry about calibrations on the modern machines today. How many of you actually use a calibration phantom? If you do, answer yes. If you don't, answer no. I would suspect that it's a relative minority. In general, instead, what we do is we just place a region of interest in an area where we know there is no flow, such as in the lungs, to make sure that it's zeroed at this level, and we can reliably accept the measurements within the vessels. The examination is performed with gating, and we can do this in 2 different ways. We can either do this as prospective triggered or retrospective gating. The advantage of the prospective is we can define the acquisition window, and it doesn't change from beat to beat, whereas retrospective gating, the acquisition window is continuous throughout the cardiac cycle. The prospective gating, therefore, can have an advantage when there's arrhythmia, since we can set the acquisition window shorter than the shortest period of R to R with arrhythmia, and therefore we don't have any chance of arrhythmia causing artifact within the images. However, the disadvantage is because we are shortening this acquisition window, we are not capturing the entire cardiac cycle. For the most part, this doesn't cause any significant issues as we generally still have in diastole and in systole, but there could be some issues because we would be losing part of the diastolic phase. You can also perform it with breath hold versus free breathing. Obviously, the advantage with breath hold is there is no motion artifact from breathing, and therefore the overall acquisition time is also shorter because it's performed during a breath hold. However, the temporal resolution is compromised when performing breath hold. As the old saying is, you get nothing for free with MRI. Therefore, because your overall acquisition time is shorter, your temporal resolution is compromised. So with the free breathing, you may have artifact from the motion, however, you do have a higher temporal resolution. Which technique do you most commonly use for flow imaging? A, breath holding, or B, free breathing? When we perform flow measurements, we need to pick a velocity that we expect to be the highest velocity of blood flow within the image plane. The closer the velocity encoding value is that we pick, the more accurate our measurement. We, in particular, do not want to pick a velocity encoding that's too low because that'll result in aliasing. So as you can see here, if we pick a velocity encoding that's 150, that means that we're going to be able to accurately represent velocities that are 150 centimeters per second in one direction or the opposite direction. But let's say we have flow that looks something like this, where we have a velocity that's higher than 150. Well, since that velocity that's higher than 150 can't be mapped, it actually wraps around and is mapped at the bottom with a negative velocity. So this is aliasing. So in this situation, what we would actually need to do is we would need to increase our velocity encoding to 250. And if we increase our velocity encoding to 250, then you can see that the full curve is able to be mapped in the correct direction. And we don't get velocity in the positive direction that because of the high velocity is encoded in the negative direction. Velocity encoding can be performed in the in-plane or through-plane method. In the in-plane method, basically what we're able to do is look and determine the direction of flow. So if we have eccentric jets, it's a good idea to kind of look at the in-plane velocity images to be able to predict the direction. However, the majority of the time we're going to be using through-plane imaging, and this is the technique that we'll use when we actually want to do quantification. But in order to do good through-plane imaging, we have to make sure, regardless of the direction of the jet, that we are truly perpendicular. So we may have to set up some unusual double oblique images in order to get good through-plane quantification. You can see on these two images, here's a magnitude and a phase image of aortic coarctation, and you can just see that we've laid out the aorta, so we have a long axis basically image showing the flow, and we can see the direction within the long plane. The majority of the time, as I said, we're going to use actually through-plane imaging, and here we've set up a double oblique just above the level of the aortic valve to look at flow through the aortic valve. And here again we have magnitude and phase images looking at flow through the aortic valve. Once we have those images, then we're going to load it into whatever software we have available, and we're going to actually do our quantification. So what we need to do is find a good image, create our region of interest around the vessel. In this case, we're looking at the aortic root, and we want to make sure that we include any flow that's within the aorta, but not any flow that's in the adjacent outflow tract of the right ventricle or the SVC. And then we want to make sure we look at each image throughout the cardiac cycle and make sure that we do have just the aorta included. And then we can get our summary and see what our actual peak velocity is, what our forward flow is, and what our reverse flow is. A couple tips to keep in mind. Make sure that your spatial resolution is appropriate. You want to make sure that as your vessels get smaller, you have a much higher spatial resolution, and that'll prevent partial volume artifact in your flow measurements. Also, if you have very high flows, you want to make sure that you have a higher temporal resolution to more accurately catch those peak velocities. Also, if you're looking at regurgitation at the level of the aortic valve, a subaortic valvular slice actually will work better and give you better representation and more accurate numbers than a slice just above the aortic valve. MRI is the reference standard, the gold standard for volume and mass. It's accurate, highly reproducible, and does not make many of the geometric assumptions that other modalities such as ultrasound make. It does have some limitations. In particular, you have to keep in mind that the heart is not only squeezing in the short axis, but it's also moving along the long axis. So that means you have to keep in mind when you're doing functional analysis that you may have more slices on in diastole than in systole. Another thing to keep in mind is if you do RV function, which the majority of time we don't, although there are certain indications where we will, that there's at least some data out there that shows that using axial slices rather than short axial slices may actually be better for performing functional analysis of the RV. When you're performing your functional analysis, you may want to use an automated or semi-automated technique. Most of the time you're going to use a semi-automated technique, which basically means you're going to let the computer do the first approximation, but then you may have to intervene and do some manual cleanup. The computer has multiple geometric and statistical models that it uses to try to find the edges and identify the endocardial and epicardial border. The epicardial border generally is more complex and more difficult to detect than the endocardial border because of adjacent structures such as lung, RV blood, epicardial fat. And so model-based segmentation methods generally are the most successful. The other thing to keep in mind is that CT data is shown to be very comparable to MR with respect to volumetric and EF measurements. So here we've loaded our functional stack, our short axis functional stack into our software. I've already done some of the segmentation and I just want to give you a flavor here. So what you can do is you can find your end diastolic and your end systolic phases. Then you're going to find your base slice. So you want to find the first slice that you're going to start with. And you're going to start and you're going to identify the endocardial border. And then you're going to go and you're going to find the epicardial border. And once you draw, then you may let the computer do some cleanup and create a little bit more approximation. You're going to do this on each slice of end diastole. You can see I'm just doing the first two slices here. I've already performed the analysis on the other slices. And then once we do that, we're going to switch over and do our end systole. You can see that in this situation, it didn't quite line up with the epicardial border, so we're using a manual technique to fix the edge of the epicardial border. We're switching over to end systole. You can see because the heart is shrunk in the long axis that we're actually using one less slice. When we go to do our functional analysis here, we've started on the third slice instead of the second slice. And we're also doing another slice here, again looking at the endocardial border, and then looking at the epicardial border, and then having it do a best fit. Once we're done with every slice of the endocardial and epicardial border of end diastole and end systole, we can actually pull up a graph here and you can see we have graphs. We also have a table that gives us all of our numbers, and we'll look at these numbers a little bit more in detail. As far as the myocardial mass, you might wonder how we get myocardial mass from what I've shown you. Basically, we have an area by looking at the area between the endocardial and epicardial border. We're going to multiply that by the slice thickness, and that'll give us our myocardial volume. Then we multiply our myocardial volume by our specific gravity, 1.05 grams per milliliter for myocardial muscle, and that'll give our actual myocardial mass. In general, we're going to include the papillary muscles as part of the ventricular chamber. However, keep in mind with hypertrophic cardiomyopathy, you may want to consider the papillary muscles as part of the myocardium rather than as part of the ventricular chamber. This can help prevent underestimation of myocardial mass, overestimation of left ventricular diastolic volume, and underestimation of the left ventricular ejection fraction. Now, I warned you a little bit about some math, and here are a few equations. Again, they're relatively simple. Keep in mind that the ventricular ejection fraction is just the end diastolic minus end systolic volume divided by the end diastolic volume. The stroke volume is just the end diastolic minus the end systolic volume. The cardiac output is just the stroke volume times the heart rate. And the cardiac index is just the cardiac output divided by the body surface area. So now let's move into the clinical applications and finish up in our next 10 minutes. So here are some different clinical applications. We'll talk about some of these. I won't talk about diastolic dysfunction, looking at the E to A ratio. That's basically just looking at the flow curves you get across the mitral valve. Pericardial disease, that's really just related to function. And pulmonary hypertension, which the key thing here is not only left ventricular, but right ventricular function. So if you can perform function, pericardial disease and pulmonary hypertension have nothing special. So we'll look a little bit about the other 4 indications. Now let's look at stenosis to begin with. So as I showed you earlier, you're going to draw your regions of interest around your area where you want to perform your flow analysis, and then you'll get this information where the dot here shows you what the peak velocity is. So I want to introduce the simplified Bernoulli equation, which basically demonstrates that a pressure gradient across an area of stenosis can be calculated by multiplying 4 times the velocity across the area of stenosis squared. So 4v squared. And that'll give you the millimeters of mercury of gradient, and the velocity is just encoded in meters per second, not centimeters per second. So let's look at a real-world case. So here's a case of true FISP cine images demonstrating an aortic stenosis with a bicuspid aortic valve. We now perform our flow analysis at this level, and let's look. What is the artifact and how is it resolved in this situation? Would you increase the velocity encoding value, decrease the velocity encoding value, increase the distance from the aortic valve where we're acquiring this slice, or decrease the distance from the aortic valve where we're acquiring this slice? So in this situation, what you can see in the images with the velocity encoding 150 centimeters per second is that there's black in the middle of white. That tells us we have aliasing, which we talked about earlier. So if we increase our velocity encoding value to 300 centimeters per second, 3 meters per second, then we end up with just white as the blood flows out of the aortic valve, and we don't have that aliasing secondary to a velocity encoding value which is too low. So now, what is the gradient of the aortic stenosis? Is it none, mild, moderate, severe, or critical? So in this situation, it would be mild, because as you saw, the velocity is less than 3 meters per second because we didn't have aliasing on the 300 centimeter per second image. Therefore, the velocity has to be less than 3 meters per second, and therefore the aortic valve stenosis, based on the data that I'm showing you here in this slide, less than 3 meters per second, it's mild. So 2.5 to 3 is mild, 3 to 4 is moderate, and greater than 4 is severe. This basically applies to both the aortic and the pulmonary valve. The opening area can also be used when looking at the aortic valve. If the opening area is greater than 1.5 centimeters squared, that's mild. If it's 1 to 1.5 centimeters squared, that's moderate. And if it's less than 1 centimeter squared, that's severe. Here's a case of aortic coarctation. You can see the flow in the descending aorta on the phase image where there's a black jet. And we can do quantification at this level, and we can see that the peak velocity at the level of the jet in the descending aorta was almost 4 meters per second, 396.5 centimeters per second. Therefore, if we plug it into the simplified Bernoulli equation, we get 4v squared. That's 4 times 4 squared, which is 4 times 16, or 64 millimeters of mercury gradient. Now, if the aortic coarctation is combined with an aortic stenosis secondary to a bicuspid valve, where the velocity of blood coming out of the aortic valve is greater than 1 meter per second, then we have to use a slightly more complicated formula. In this situation, we take V2, square it, minus V1, square it, and then take the difference of those two and multiply by 4. So if you had a velocity coming out of the aortic valve that is greater than 1.5, you would square that and subtract that from the 16 and then multiply by 4. So you have to correct if you have accelerated flow coming out of the aortic valve greater than 1.5 meters per second. Regurgitant valves. Here we have the pulmonary artery that we're showing in cross-section. We have the magnitude and phase images. And what you can see on the image, the phase image on the right, is that we have white followed by black. Now remember, we don't have white in the middle of black or black in the middle of white, so this is not aliasing. This is basically to and fro flow across the valve. So when we do our analysis where we draw a region of interest, we get a flow curve that looks like this. So you can see that there's forward flow, there's reverse flow, and then it comes back. And so this reversed flow is our area of regurgitation. The area under the curves gives us our forward volume and our reversed volume, which you can see here, 113 milliliters forward, 64 milliliters reverse. So when you take that ratio, you get a regurgitant fraction of 57%. So what is the grade of the regurgitation? Is it none, mild, moderate, or severe? Well, in this situation, we have greater than 50% regurgitation, therefore it's severe. So less than 30% is mild, 30 to 50 is moderate, and greater than or equal to 50% is severe. Here's a situation where we've got mitral regurgitation. You might just think we can put a plane across the mitral valve and look at the flow. And in this situation, it probably would work given that the jet is relatively perpendicular to the valve. But many times the flow is eccentric along the surface of the valve. And remember, your imaging plane has to be perpendicular to the flow jet in order to get accurate quantitative values. So, what two values will allow calculation of the mitral regurgitant fraction without acquiring data at the level of the valve? The right ventricular stroke volume and aortic forward flow, the left ventricular stroke volume and aortic forward flow, the right ventricular stroke volume and pulmonary forward flow, or the left ventricular stroke volume and pulmonary forward flow. Well, remember that the stroke volume is going to equal the aortic forward flow plus the mitral regurgitation. So basically, the blood is being squeezed out of the left ventricle. That's the stroke volume. It can either go out through the aorta or it can go backwards through the mitral valve. There's no other place for it to go as long as there isn't like a VSD. The stroke volume minus the aortic forward flow equals the mitral regurgitant volume. So the mitral regurgitant fraction equals the mitral regurgitant volume divided by the stroke volume. So if you know the aortic forward flow and you know the stroke volume, you're able to calculate the mitral regurgitant fraction, and it doesn't matter how eccentric the jet is. Cardiomyopathy, obviously with cardiomyopathy, we can evaluate the myocardial mass. We can also look at the function. I've already shown you how to do that. But the other thing we can do is we can look when there's septal hypertrophy and there's obstruction of the left ventricular outflow tract, we can look at the gradient across that. So we can place a plane across perpendicular to the area of stenosis within the subvalvular LVOT, and then we can do our quantitative flow assessment at this level, and we can calculate what our gradient is. So what is the gradient across the subvalvular stenosis? Is it 6.25? Is it 25, 36, or 196 millimeters of mercury? Okay, so you can see that our peak velocity here was 2.5 meters per second. When we plug that in, 2.5 meters per second squared is 6.25, and we multiply by 4, we get 25. So 25 millimeters of mercury is the correct answer. The last thing I want to talk about is congenital shunts. Here we have flow through the aortic valve and flow through the pulmonic valve. We can draw our regions of interest and get our flows. You can see here we have our forward flow through the aortic valve of 104 milliliters, flow through the pulmonic valve of 144 milliliters, and so when you do a QP/QS, you get 1.4. So this is a left to right shunt with a ratio of 1.4. In general, 1.4 to 1.5 is when shunts start to become clinically significant, and when they're greater than about 2.2 is when they're considered relatively severe. So, as Yogi Berra said, it's like deja vu all over again. Here are the learning objectives, so I hope that now you can prescribe a scan, do the analysis, including the functional analysis and flow analysis, and know at least 3 clinical use case scenarios for flow and functional analysis. Thank you very much for your time, and if you have any questions about this presentation, feel free to send me an email. Thank you.